Cool. I think we can get started. Thanks everyone again for coming to our tutorial and hope you have listened to the awesome talks given by previous speakers. I'm Linjie, a senior researcher at Microsoft. And in this talk, we'll be having a journey together on multimodal agents. If we were lucky enough to have you for our CVPR 2023 tutorial, we also covered multimodal agents. For that part, we primarily introduce multimodal agents that chains multimodal experts with large language models, where the user interacts directly with the large language model. It serves as a brain of the agent. It has access to abundant tools, which can be open source models, provide private or public APIs, or code interpreters. And the large language model will do the planning to plan which tools to use and in what order. It gathers information from the tool execution and summarizes them to respond to the user. We have many show agents like Visual ChatGPT and MMReact, where the goal is primarily to enable the blind large language model with multimodal perception, understanding, and generation. All this have been nicely summarized in our survey paper, which we wrote right after the CVPR 2023 tutorial. But since then, we have also seen rapid progresses in large multimodal models. Take the MMVet benchmark as an example. We see the open source model improves from 20-ish to 62.8 and getting close to GPT-4v. In addition, we also saw GPT-4o just a month ago, which is a naive multimodal model that can perceive and understand the multiple modalities, including audio, visual, and language. So the question arises, now that we have so much stronger large multimodal models, do we still need multimodal agents? And in this talk, I'll be introducing 3 advanced multimodal agent designs: agents with multimodal memory, actionable agents, agent with feedback, and also demonstrate its application in tasks where to date, single large multimodal model still cannot yet solve. So first, let's take a look at agents with multimodal memory. So I would like to justify it, why agents need multimodal memory with the challenges in video understanding. Let's first take a look at the video here. It's ads about accessibility.
People think that having a disability is a barrier. But that's not the way I see it. You can catch up with friends.
Ready?
You can capture a moment with your family.
One face, small face, focus lock.
And you can start the day bright and early. You can take a trip to somewhere new. You can concentrate on every word of the story.
A bird began to sing.
Cool. So you see the videos have a lot of frequent scene changes. It's not about one character, it has a lot of character and it's telling a story, right? So to fully comprehend the visual signals in this video, one may need densely sampled frames, which will lead to long sequence input with many tokens. And that means high inference cost, latency with even a single pass to the large multimodal model. And not mention that the explosion in the memory cost if you want to encode and process everything all at once. So that's why we need memory. And why multimodal? Because videos are naturally multimodality with non-speech audio, like the music, speech, visual signals, and with speech, we also need like language understanding. But one may argue that nowadays, there are so many video QA tasks, and we're seeing like large multimodal models without a memory already perform quite well on these tasks. So let's take a look at a very challenging but high-value video understanding task. It's called audio description. Audio description is the verbal depiction of key visual elements in media and live productions, meaning that it needs for streaming and non-streaming videos. And it's meant to provide blind and visually impaired individuals from gaining a complete understanding of the given program. So it is a very representative and challenging visual understanding tasks in real life scenarios. It tests for long multimodal context understanding, and that's why we need multimodal memory. It also tests for coherent generation. So what has been said before in audio description, you don't want it to repeat it all over again, right? So it requires a memory of what has been mentioned before. It also requires decision-making about when to say what. You don't want the audio description to overlap with the speech signals that are already in the video. What about using an agent instead of a large multimodal model to solve audio description, right? Now, I hope both you and I agree that we have to have multimodal memory. So revisiting the original agent framework we showed just a few slides ago, now it becomes this, where the brain of the agent has access to memory. And similar to humans, agents should have both short-term and long-term memory. And here is an example of an agent with multimodal memory. In Narrator, we design an agent of narrating long-form videos with both long-term and short-term memories to generate audio description. The short-term memory just contains the most recent AD predictions from the previous round. The long-term visual memory contains all previous frames and the previous predicted ADs. And given the current frame, we will calculate the frame similarity and retrieve the most relevant AD predictions from the previous rounds and use them as multimodal in-context few-shot examples to generate the current AD. So for this talk, I'll just show you one example. If you're interested, this work is also will be having a poster session on Thursday morning. With the same video I showed you before, now we add AD from Narrator. Let's take a look.
White kitchen, cabinets and sink, oval mirror on wall.
People think that having a disability is a barrier.
Woman in discomfort, being moved in seat.
But that's not the way I see it.
Document on screen, man takes selfie.
You can catch up with
A
friends.
selfie with woman's face on phone screen.
You can capture a moment with your family.
One face,
Family having picnic,
small face,
father taking photos.
token block.
Father checks phone with worried expression.
And you can start the day bright and early.
Woman checks phone in bed, moves to wheelchair.
You can take a trip to somewhere new.
Male leaves cabin, close up of red hearing aid. Man adjusts hearing aid settings.
You can concentrate on every word of the story.
A bird began to sing.
Okay, I'll stop right there. But the full visual examples is accessible through the website. So though the generate AD is not perfect, right? Like the visual scenes are not always in sync with the AD we generated, but it does tell a lot about the visual elements for accessibility. So audio description is indeed a very important and high-value video understanding task. In addition to that, in MMVid, we show if prompt for more descriptive generation, we can convert video understanding into a long document understanding. So for each scene, we similarly leverage multimodal experts such as ASR and ask GPT-4V to generate ultra descriptive captions. And the scene descriptions combined with external knowledge, with metadata, title, abstract, or character snapshots, etc., will be fed into GPT-4 to generate sync script. By sync script, I mean like it contains both the starting and ending time steps of a sequence of video segment in the scene, and the description of what has been happened in each segment, exactly like a movie script if you want to direct a movie or shoot a movie. So gathering all scripts for different things, we generate the final script for the entire video. That will become a long document. And this script can be used as the basis for performing various video understanding tasks. So in MVid, we showcase its ability to handle various video lengths and domains, and how it is capable of solving various granularities of video understanding tasks, not limited to audio description. For example, it can summarize hour-long videos, cross-reference multiple TV episodes. Also, it can perform fine-grained tasks like character identification, speaker identification, and ground QA. And next, we'll show highlights, some highlights on its ability or its potential to act as actionable agents. So in case study 1, we show how it is able to understand ecocentric video, which is really the basis of embodied AI agents. So as I mentioned, MMVid will first generate a long script of the whole video content, which is hidden from the user. And when user asks, where can I find my pink jacket? It responds with, your pink jacket can be found on the chair covered with clothes. And next, user is wondering, when did he or she pass by the chair? And Vid grants it to the time range of 5 to 6 seconds into the video. Let me see if it can play. Okay, 5 seconds. There it is, the pink jacket theater chair. Okay, sorry about that. So in the second example I want to show is how MVid can help co-piloting games. So this is completely MVid playing this Mario game. So we streaming in the input, and the generated script for each step is just based on the history frames. And to complete this task, we prompt MVid to directly predict Mario's next action. Could be like jump, jump left, jump right, jump up, or pause, or duck, or something. And once Mario takes an action, the resulting game screenshot will be sent to MMVid again to refine the script for the next action prediction. Hope that was a fun video to watch, but we did not run long enough to see if we finally rescued the princess. And the Mario game showing that video was fairly simple, right? If you play Mario games nowadays, it's quite complex and the graphical design is much, much better. But what is more complex is GUI navigation. Well, the task can be AI companions that helps you with business tasks, personal AI assistants that aids you in like daily tasks like reading your email or something, or even office automation that frees you from making the slides for this talk. And the action space we explored in Mario game is also simple, like jump left, right, jump with left, jump with right, etc. In GUI navigation, we have click, type, select, drag, and for each one of them, there are so many more options on the screen in terms of like what and where you should be clicking, right? So that requires next level understanding or grounding capabilities that than what has been seen in the Mara video. Okay, let's revisit this framework again. Last year, we mostly shown tools that operates on static inputs, for example, image or video, which does not change as we execute the tools. And for actionable agents, we need an interactive environment. And the tools can directly take actions to change the environment. So our observation of the environment will change with it. So that opens our new next chapter of this talk, actionable agents. There are indeed so many more possible interactive environment than GUI navigation. For example, what have been covered in Jenwei's talk about embodied AI autonomous driving. But in this talk, we'll take GUI navigation as the exemplary task. And in case you haven't forget, just 30 minutes before, Joey has introduced a set of mask prompting, in which if you leverage segmentation models to find the salient objects or regions and tag them with numbers or letters, it aids GPT-4V in visual grounding. And what if we take advantage of this prompting technique and use it for GUI navigation? I think you already know the answer, but we'll dive deeper into the agent design. So taking advantage of SLM prompting, we built Navigator, a LMM agent for GUI navigation. So it has two key features. First, as it leverages a set of mask prompting, it connects the text output of GPT-4V to the action space of like where you can click on the screenshot, right? Without the SLM prompting, it might be difficult in describing where exactly the agents need to click, especially like we know GPT-4V is so bad at grounding. So now it just needs to speak out the tag number. Once it predicts the action with the associated tag, we also have a phase. Sorry. Okay. I think we need to mute others or something. People joining on Zoom, can you mute? Okay, I mute them. Let's continue. Yeah, so we have a phase two, where the agent needs to summarize the history of the first T steps, and we'll use that as context when prompting for the prediction on the T+1 step. That sounds a little familiar, right? So it's like a memory. And we conduct human evaluation on the agent's performance on iOS for a single step. Over 90% of the time, we see like GPT-4V can output the intended action description, so click on what. And about 75% of time, it can localize the action execution, so be right about where to click. So here is a demo of Navigator performing a sequence of actions. The task is, we now need to shop for a milk frother, and the budget is $50 to $100. So it first starts with, okay, I don't see an Amazon app. And you notice it's hidden on the finance group, which is tagged with ID 16. Click on that, entering the finance group, seeing the Amazon app tagged with ID 6, entering Amazon app, now need to type in the search bar, which is ID 5, and search for the milk frother. Once search for the milk frother, now we need to do filtering, which is ID 8. Click on the filters, entering the filter page. Now limiting the price to be $50 to $100, which is ID 26. And once filtered, click on all results, ID 13, to show all the results after the filtering. And among the three results displayed on the phone screen, it says it's perfect milk frother, which is ID 7, and which is within our budget because it's 59.95. And now clicks on buy now. And lastly, clicks on ID 3 to swipe to place your order. Okay, that's a cool Navigator demo, but what's beyond Navigator? Navigator is based on GPT-4V, and we don't see a live one. Maybe it's because of the latency. So can we build agents with open source, small, large multimodal models that is lower cost, low latency? If you listen to today's previous talk, you might already know the answer. So to empower open source models for GUI navigation, we have two routes. The first most common approach is to enable it with grounding capability on UI interface. For example, training a model like Cog Agent or Ferret UI that can ground a referring expression in the screen. And another alternative is distill SOM prompting to a smaller model, right? So in SOM Lava, we explore how we can enable Lava to comprehend SOM prompting. As an initial exploration, we conduct our experiment on the general visual understanding of natural images and show that it can successfully recognize the number tags, so produce more accurate responses in visual recognition and grounding. And another very important direction beyond Navigator for GUI navigation is evaluation benchmarks. In this space, we propose a new benchmark video GUI that focuses on video-centric GUI tasks with long procedural planning and allows for testing with interactive environments. So existing GUI benchmarks mostly focus on simple tasks that can be clearly described by textual query. Where in video GUI, we focus on video-centric tasks, such as create the below effect in PowerPoint. Clearly, this jungle slide with the animation effect is harder to be described comprehensively in that language. So to create video GUI, we explore 10 visual-centric software that are used for media creation and editing. We also include novel software, for example, AI tools like Stable Diffusion or Runway. We source high-quality instructional videos online that teaches average users to complete complex and novel tasks with these tools. And based on the video, we have a human annotator that watches the entire video first and reproduces it offline. They are asked to provide 3 levels of annotations. So for the high level, they break down the full task into several subtasks, where each of the subtasks will be one milestone of the whole process. For middle level planning, which annotates each subtask with a sequence of action narrations. And lastly, for the atomic action execution, we record the annotator's actions with the simulator. So you will have the coordinates of the user actions and later use that for evaluation. And for evaluation metric, existing benchmarks usually use a 0 or 1 successful rate as the metric, which you find that for complex tasks like in those in video GUI, the success rate is easily 0, which does not provide enough information in terms of what the when and where the agent or the model fails. So with the high quality annotation in Video GUI, we propose a hierarchical assessment where we evaluate different levels of procedural planning and atomic action execution separately. And even in atomic action execution, we separate out the different types of actions to evaluate the model. And in our experiment, we benchmark SOTA large language models, large multimodal models, as well as large multimodal models with tools. You would think that action execution, which requires grounding, is quite difficult for these models. But we find that planning is actually way harder, especially the high-level planning, which breaks down the full task into several subtasks. And inaccurate planning definitely would lead to subsequent failures. So that will lead to the zero successful rate. And another observation we will want to highlight is even the SOTA large multimodals to date, GPT-4o, still need tools like OCR or set of mask prompting to perform better on action execution. And in Video GUI, we also build a simple agent baseline with GPT-4o, where GPT-4o will first make the high-level planning, and based on its high-level plan, it makes the middle-level plan that narrates a sequence of actions to take, and use GPT-4o plus OCR to do the execution. So once an action is taken, the state transits, and the observation is sent to the planner again for the next step. And we evaluate this agent on the PowerPoint tasks and show that even with the ground truth planning, the successful rate on the full task is still zero, which supports our motivation on more fine-grained hierarchical evaluation to pinpoint where the agent fails. And on subtasks, the agent without GT plan only achieves 20% successful rate. And while GT plans can boost it to 50%, but an observation we want to highlight is that the generative plan from GPT-4o on average needs 2 more actions than the GT plans. Okay, next we show qualitative results with our simple agent baseline. Here is the preview of the final goal. So basically we need to create a slideshow that have some kind of animation of a 3D dog. And let's take a look how the agent performs. So it starts with a blank slide. Need to insert a gradient fill background. Just click on design, click on background. By the way, green means correct. So gradient fill fills the background. Then click on insert. Click on the 3D models. Click on stocks 3D models. And then type dog, then enter to search for a 3D model with dog. Okay, now need to select the Shiba Inu dog with motion. This is where it makes the first mistake. Instead of choosing a 3D model with motion, which is exactly describing the first plan, it chooses a static 3D model. It's a little hard to tell the difference, but the running person logo at the bottom left indicates it's a 3D model with motion, but it chooses a static one. Okay, continuing, it inserts a run 3D model, but let's see what happened next. Okay, now the instruction is drag the dog to the top left. It fails to drag to a proper location and didn't release it when it's near the right location, so it stays on the center. And now it's dragged the lower right corner to enlarge the dog. Apparently it didn't localize the right corner correctly, so that's where it makes the third mistake. We already see 3 mistakes made by this agent, but we will stop here for detailed analysis. Next, we just compare side by side versus a human agent. Both have the GT planning. They are just doing action and execution. So let's wait for the final product and then see how it looks like compared to human agent. By the way, like humans for this example takes only about 4 minutes to reach the final product, while the GUI agent takes more than 2 times longer. Of course, we didn't do enough system optimization and it is doing the API call to GPT-4o, but still like it takes quite longer than the human agent. Okay, I think that's pretty much it for the GPT-4o agent. Oh, so first it inserts inserts in the wrong place for the title. And now there is also no side view slide, a second slide. So you can see like how it's still not there yet for this complex task. So one might think, what if the GUI agent can revise its plan, right, as it executes, and or its action based on the outcome of the previous action, right? And that leads to the last part of our talk. It is the same framework again, and this time the brain of the agent can receive feedback from the interactive environment and use it to revise its plan. And in this part, we'll introduce idea to image, an agent with feedback for visual design and creation. So first, why agents need feedback? As humans explore unknown environments and the problems all the time, and the approach we usually take is to iteratively doing self-refinement during our exploration. We consider multiple proposals, evaluate them, maybe mimic them with our own like word model, select the best one, execute, and receive feedback from the environment. So inspired by this, we designed a GPT-4v powered agent system with iterative self-refinement to prompt the text-to-image generation model for automatic visual design and creation. First, let's introduce what is visual design and creation. Differing from text-to-image, visual creation can be with multimodal idea inputs, instead of the text-only inputs in text-to-image generation. The multimodal idea inputs can also be of arbitrary form, instead of just the detailed image descriptions in T2I. And visual design also requires better visual and semantic quality. For example, in this case, it needs to capture both the style of the bottom left dog image and also preserve the semantics in the upper right image. So to achieve the automation of visual design, idea to image leverages GPT-4v for each step in its execution flow. First, for prompt generation, it includes initial prompt generation and also revised prompt generation in following iterations when provided with feedback. Second, after the T2I model generates multiple draft images, like in Midjourney, you get 4 at a time. GPT-4v is instructed to assess these candidates and select the best draft image that is closest to the requirement. Third, it reflects on its selection. If the draft image is still not fitting the requirement yet, it provides feedback on the errors and the revisions directions in text format, which will be again used in step 1 for prompt generation. So the agent also has access to a memory, where all the previous rounds feedbacks, best images, and best text prompt and original user requirement is kept there as context for prompt generation. So we show some qualitative example of comparing single round human prompting to iterative self-refined idea-to-image prompting, we see that idea-to-image clearly can produce images with better visual quality and a high semantic alignment to the user requirement. For example, for the first example, for the logo of, I don't think it's CVPR conference, but a conference happening in Seattle. It gives more accurate syntax generation for the conference logo. The third example, the second example, it shows simple line design with llama in the same style as the user provided image. The third example, it gives the correct dog breed and position. And the last one, it can have the exact right you got pose and the style in the last one compared to the single round human prompting. And in addition, all these examples clearly show the challenges in visual design and creation, where most of the time the user requirement is hard to be described in text alone, hence leading to the failure of single round human prompting. So while our idea to image with self-refinement can lead to clear improvements of the result. And we conduct human evaluation comparing the initial round of human prompting versus initial round of idea to image prompting and the final iterative refined idea to image prompting. Across different T2I and I2I models, we consistently observe higher user preference score on all these generation models. And we see that the stronger generation model is, they benefit more from ideal to image iterations. So in ideal to image, we had an agent case study on the automatic video design and creation, viewing the text to image as an unknown environment and mimic the iterative self-refinement view via GP4V based agent system. So this self-refinement schema relies on receiving feedback from interactive environments, which can also be extended to GUI navigation, embody AI, image to code, and so on. And agents can also think twice or self-evaluate its own output, even without receiving feedback from the environment, which is called self-reflection and has also been explored in the agent designs. So remember the question we raised at the beginning of this talk? Do we still need multimodal agents? And I hope you arrived at the same answer as I did. Yes, we do. In this talk, we have shown 3 advanced agent designs with its applications, right? Agents with multimodal memory for audio description, actionable agents for GUI navigation, agents with feedback for visual design and creation. And the scenarios covered in this talk to date are still difficult for a single large language model or large multimodal model to tackle. And the ultimate goal of having multimodal agent, in my own opinion, is to aid humans in performing tedious tasks, such as like in GUI navigation for maybe replying emails or creating slides, and prompt engineering in the visual design and creation, or to use AI for the greater good, for example, like better accessibility. Imagine we have audio description enabled for all the videos we can see online. And one last piece of evidence is that even on non-agent targeted benchmark like MMVet, the current #1 is also a multimodal agent, beating GP4O by 5 points. I want to bring you back to this framework again, recapping the advanced designs we have covered. We added memory to the framework so that it can keep a longer context for more coherent predictions. We show how agents can take actions in interactive environments and take advantages of the feedbacks to refine its output. However, if you haven't noticed, the tools in the agents we covered today or a year ago mostly are still lightweight, much more lightweight than the brain of the agent, the large language model or large multimodal model. So alternatively, researchers have also started to explore using other large language model or large multimodal model as tools. Also, we can take out the user interactions entirely, having LLMs or LMMs to interact with themselves, which is often referred as multi-agent system. So apart from the agent system design, as agents evolve, as the parallel advances in evaluation is as important as modeling improvement. We recently have also introduced another evaluation benchmark, MMWord, for multidiscipline, multifaceted word model evaluation in videos. And the current state of agents are far from perfect, given by the near zero successful rate we see just before, and also what Jeremy mentions about GUI navigation, still far from being a parallel to human. To improve agent, not only we need to improve models, but we also need a lot of system optimization to make it actually useful. For example, for faster speed, for higher accuracy, and for better privacy. We definitely do not want an agent that lives on our computer to pick into our private information. And existing agent systems take so much advantages from the advances in foundation models. Can agent help improve large language model or large multimodal models? So in my opinion, agent exploration and exploitation are valuable synthetic data to use as training data. Oh. Cool. Yeah, I think I'm also done. So that actually concludes my talk. And given the time, what is time now? I think we should have a break. Yeah. So thank you guys very much for listening. If you have questions, you can just directly comment up and